Hello, everyone. I hope you're ready to dig back into physics. By now, the first 9 weeks is ended, and we are starting our very uh, newest unit, or I'll say just our newest unit. It's titled "Motion in Two Dimensions." Motion in two dimensions, or kinematics. Oops, if I could spell this morning. Kinematics in two dimension. Now, what is kinematics in two dimension? Oh, and by the way, at this point, if you haven't learned by now, in these videos, you should probably be taking notes as you're watching them. So if you're not already, just pause the video, go get something to take notes, come back and follow along with me and write down any essential information because, I allow notes on the test. So whatever you write down here in this video, you don't have to go back and reference it while you're taking the test. You can have your notes ready. So let's be sure we're doing that. But anyway, side note ended. The motion in two dimensions. So what does that mean? Well, previously we talked about kinematics in one dimension. Kinematics in one dimension. That means that the object was either going left and right, or the object was either going up and down, like in our free fall kinematic problems. It was either or. Well, in this one, we're going to have objects going up and down and left and right. Does that look familiar? Look at that. Remember from your math classes, this little guy, the coordinate plane. It's supposed to be an X there. Coordinate plane. So we're going to look at kinematics of a moving object with both an X, a horizontal, and Y, a vertical component. So where do we see this? Where do we see that? Well, if you can look over here to the left, you'll see that the first topic we're going to talk about dealing with motion in two dimension is projectile motion. Projectile motion. So what is projectile motion? Well, projectile motion, you'll learn, is a parabolic path an object takes while in the air. And it consists of two dimensions. So let's say, for example, this is a golf ball on a tee. All right, that's a golf ball. Somebody hits it, it's going to have a similar path to this, right? There's other factors at play, but this is a perfect world, and it's going to have a perfect parabolic path. We're going to neglect any drag or air resistance. Okay. So what's happening is we don't just have a linear motion. We don't just have a linear motion like we did in our last unit. Instead, we have two components. We have, actually, I want to redraw this to where it makes more sense. Okay, there we go. We have, in the x direction, an inertia component. There's an inertial component that says that this ball is wanting to continue traveling in the direction that the force was, or the unbalanced force was initially applied. So if this were kinematics in one dimension, we had no other forces acting on it. Instead of a parabolic motion, the path would look like this, like that dotted line. It would just continue in a linear fashion. But that's not true on Earth. Why not? Because we have another component that's constantly acting down, and a gravity component. Okay, so in the x direction, we have inertia, and in the y direction, we have gravity. And both of these are acting at the exact same time, and that's what creates this parabolic path. So we're gonna in this unit, in this section more specifically, we're gonna learn how to break down the kinematics of this path, this parabolic projectile path um, to describe the motion of this object and to quantify the motion of this object. So that being said, uh, let's get into projectile motion more specifically. Let me add this. Okay, here we go. All right. So before we can do that, we have to revisit a couple of our friends from Unit 1. And they're the motion formulas or the kinematic formulas, whatever you want to call them. So let's not forget these. Write these down somewhere. Memorize them if you want to. They'll always be provided for you on a test and a formula chart. But just know that they're not going away. And if you haven't figured out how to solve problems dealing with these formulas, then now's the time, because in these problems, you're not just going to be dealing with kinematics in one direction. It's going to be two directions at the same time. So you're going to have a couple things going on when you're trying to work these problems. So let's be sure we know how to work those and we know how to use them. And don't be scared of them. A lot of students are scared to do the math that goes in that involves these kinematic equations. Just go at it, and if you get stuck, reach out to me or a peer, and we'll help you. Okay. Okay. So here's a few things about projectiles. So in introductory physics, and in high school and even in college physics, introductory college physics, we're just going to neglect air resistance, right? Welcome to Newtonia. That's all I like to say. Right? We're going to neglect air resistance. So therefore, as I said earlier, the path of projectile is a parabola. So if you neglect air resistance, you throw a football up in the air, it's going to have a parabolic path. Whoa, that was not good. No one said I was an artist. It's going to have a parabolic path. We'll assume that's a good parabola. And it's going to be a symmetrical parabolic path. Okay. So let's look at this and break it down into horizontal and vertical components. Let's look at the horizontal. Right, the horizontal. This next bullet says the horizontal motion is constant velocity. Okay, so when we're talking about projectiles, let's say we have a ball in the building and somebody kicks it. Right, somebody kicks it and a force is applied and it travels this path. Well, in the horizontal direction, or the x direction, velocity is constant. So it's going to have the exact same velocity through the entire through its entire path in the horizontal direction. So v of x is constant. So therefore, the acceleration in the x direction must be 0, because if velocity is not changing, then it is not accelerating. So in the x direction, acceleration is 0. So keep this in mind when you use your kinematic equations, because if a is 0 in these, when dealing with horizontal motion, you could just like cross these out. You don't have to worry about these terms, because anything times 0 is 0, right? So in the horizontal direction, velocity is constant, acceleration is 0. Okay, now let's look in the y direction. What other things do we need to know before we approach these problems? Well, in the y direction, or the up and down, I'm going to go ahead and just write that little arrows to indicate which directions are which. In the y direction, or vertical motion, or vertical direction, the acceleration is going to be 9.8 meters per second squared. Why? Why is it going to be that on Earth anyway? Should say, why is it going to be that on Earth? Well, because uh, acting up and down, the only acceleration uh, the force that's pulling that object down is gravity. And we all know that free-falling objects accelerate towards the Earth at 9.8 meters per second squared. Okay, so whether this object was dropped or it was launched, this might blow your minds, but it's going to hit the ground at the exact same time, whether it takes this parabolic path or it takes this path and you just drop it. Because in the up and down y direction, it's accelerating towards the Earth at the exact same rate, no matter what. Okay? And I'll prove that in a demonstration later. But this is true. Okay? Always true. The next one. The vertical path, I cannot talk today. The vertical velocity at the top of the path is 0. So Vy at the top is going to be equal to 0. So let's look at this example up here at the top where I had this parabola. This one right here, okay? Let's say I was throwing the football again. I was throwing a football, and at the very top, right here, the very top of this path, the highest it's going to get, kind of the halfway point, if you will, of the path, velocity is going to be equal to 0. So for a moment, it basically comes to a stop right when it changes directions. Okay, velocity is 0. And the next thing to point out is time is the same for both horizontal and vertical motions. So time, we're not going to abbreviate it t of x or t of y. It's just t. Time is just time. It's going to be the same. It's going to be the same because even though we're breaking down into the same component, into two different components, it's going to take the same time to travel, whether it be the horizontal direction and the y direction. Okay. So I'm moving along. Okay. All right. So it says, how are these formulas different for projectiles? It says they must be applied along only one axis at a time. All right. We said that already. When dealing with projectiles, we have to apply it to one axis at a time. So in the horizontal or x direction, because a is 0, we can simplify these kinematic formulas. We can simplify them to just this. Now, this one you'll find to be very useful. But these next two, actually, let's just look at the second one. I think it's more conceptual. Look at the second one. It says Vfx, which means the final velocity in the x direction, that's what that little subscript means, is equal to the initial velocity in the x direction. So basically, the velocity at the beginning of the projectile is the same as the velocity at the end of the projectile. So the velocity at the beginning is the same as the velocity at the end. So if a golf ball is hit with an initial velocity of 25 meters per second and it takes its path, it's going to hit the ground at a velocity of 25 meters per second. So something else to note when you're working these problems. Now, in the y direction, we're going to have to keep these formulas in mind. Now, notice how I went ahead and put subscripts for both the X and the Y directions, I encourage you to do the same, because you're going to have a lot of different stuff going on at the same time. You're going to have different velocities, different accelerations, uh, different distances, and we don't want to get those mixed up. So what we do to avoid that happening is, and us substituting the wrong quantity into these equations, is we put these little subscripts. So if we're looking at the vertical or the Y direction, we're going to put a Y. Okay. So the distance in the Y direction is equal to the initial velocity in the Y direction times time. Again, time is the same, so that's why we don't abbreviate time in either X or Y. And the same thing for acceleration. So I encourage you to do the same. Get in this habit, and it'll avoid a lot of confusion. I believe in the first unit, if we had done this, just simply going, putting subscripts like final and initial, or F and I, into the V's would have saved a lot of you. But I don't think we've done that. So let's try to get in the habit of doing that, and know that we have to break it down one axis at a time. One axis at a time. You just can't start pulling numbers out of the problem and start sticking them into formulas. That's not how this is going to work. I know we want to do that, but we actually have to think about what's actually going on with the problem and what is that quantity telling me. Okay. So here we go. Moving along. Now, I gave you a lot of information. Dealing with projectiles and how to break these problems down into two components. Now let's start going into some problem solving. The first one we're going to do is projectiles launched horizontally. So what does that mean? Well, in these problems, they're not going to have a full parabolic path like that. I'm not an artist. It's not going to have a full parabolic path. Instead, what it's going to have is kind of a half parabolic shape, where something is sitting on a platform and is launched horizontally, and it goes that way, or an airplane is flying and it drops something out of the airplane, and it looks like that. Okay, those are projectiles launched horizontally, and they're going to be half parabolas. So we're only going to work at one half of the equation at a time. So when we say projectiles launched horizontally, that's what we're talking about. Okay. So here we go. A typical physics problem. Here's one you'll see time and time and again. You'll have it on your test, just different values. You'll have it on a quiz. This is what it's going to look like. So a cannonball is shot horizontally from a cliff. Okay. So it says, what do we know? So your first step, and luckily it's done for you here, is to draw a picture. Okay. First step is to draw a picture. Okay. And I'm going to try to just kind of draw the path of what this is going to look like, knowing that it's shot horizontally. And I can also draw a velocity vector, as indicated here, and d of y is going to be the height of the cliff, and d of x is going to be how far downrange it went. Okay, your displacement in the x direction is how far downrange it went. By the way, if you see range, if they ever ask you how far downrange, that's what it's talking about. All right, so we drew a picture. We kind of got an idea of what's going on. The next thing I'm going to do is write my givens / my knowns. Now, this problem hasn't given me values yet. It hasn't given me quantities, but what do I know? I know that the velocity in the x direction is going to be constant. So Vix is going to equal to Vf of x. the initial velocity in the x direction is equal to the final velocity in the x direction. I know the acceleration in the horizontal x direction is going to be 0. I know a of y is equal to 9.8 meters per second squared. And I also know, now this isn't going to come into play as much. I'll take that back. Yes, it will. Sorry, my apologies. That Vy, or V at the top, is going to be equal to 0. So the initial velocity up and down, even though it's being shot horizontally, the initial velocity in the y direction is going to be 0. Okay, so keep that in mind. Remember, at the top of a parabola, and this cliff face here is representing the top of the parabola, Vy is going to be 0. And the time of x is going to be equal to the time of y. So that's what we know. That's not what's been given, but this is what we know. So every problem that we do when we go to approach it, we know all of these things to be true. Always. Okay? So let's move on. Okay. So another note when dealing with these types of problems is remember to keep the horizontal and vertical motions separate. So remember I hope you noticed when I was writing down my givens, I kept these separate. I put over here an X with a line under it and Y with a line under it. That's how I break it down. And I put everything I know about the X direction over here and everything I know about the Y direction or the vertical direction over here. And that's where I work my problems because I don't want to get all these things confused and mixed up, and X's and Y's and all these different velocities and accelerations, because we're going to have a lot of numbers to be messing with here, and we don't want to get them confused and mixed up with one another. So be sure to separate it. And the next point, it says time is the factor that ties them together. Okay, so time is the thing that ties it together. It's the only thing, the one and only thing that the x and y direction is going to have in common. Okay, you'll see why that's important later. And the next point says, since the vertical motion is treated like free fall, and we have more info about the vertical, we should use that to solve for time first. So most of these problems, because you know more about the y direction, is going to you'll find it beneficial to solve for time doing that, because most of the time you'll have more information about the vertical, and you should solve for time first, generally, right? General rule. I won't say rule. I'll say practice. Something that you would do most of the time, but not all the time. All right. So here we go. Getting to the nitty gritty. We're doing our first problem here. It says a cannonball is shot horizontally at 5 meters per second from a cliff that is 35 meters high. Okay, shot from a cliff that is 35 meters high. Sorry, oops. What am I doing? Sorry, I had some technical errors here. So it says find the time t and the range d of x and find the final velocity. Okay, so this is what the problem tells me. I'm going to write my givens. Okay, my givens are here and my knowns are here. All right, and I'm going to break this into x and y's, and that's where I'm going to do my work. I'm going to write everything I know in the x direction and everything I know in the y direction. So I know the velocity, the initial velocity. Let me retype that. Initial velocity in the x direction is going to be 5 meters per second. I know that the final velocity in the x direction is also going to be 5 meters per second. How do I know that? Because in the horizontal direction, velocity is constant, right? That's what we said earlier. That's what we know. All right, so what else do we know? Well, we don't. We don't know anything. We need to solve for time, and we need to solve for d of x. All right, think about what we know in the y direction. In the y, we know the initial velocity is 0. The initial velocity in the y direction is 0. Because up and down, think of this as an object in free fall. Okay? Up and down. If we didn't shoot this cannonball, we just dropped it, it would start from 0. Remember that free fall problem? So initial velocity is 0 in the y direction. We know also the displacement in the y direction. Why? Because that was given to us to be 35 meters. We're given the height of the cliff. So in the y direction, the distance is 35 meters, and the acceleration is 9.8 meters per second squared, because this is essentially, in the y direction, it's essentially in free fall. So we know that to be 9.8 meters per second squared. Now, actually, I'm going to get time. I'm not going to write it under either x or y because I don't want to confuse y'all. Time is time. It's true for x and y, okay? So if we can find time in the y direction or the x direction, it would be the same for both. All right. So hopefully y'all are following along with me. Write these down. Keep them with you because we're going to use them as we continue. Now, here's our same problem. We have what we know. And let's look at this note down here at the bottom of the slide. It says, since we know more values for vertical motion, let's use it to find time with the distance equation. It says distance equation. It's just one of the kinematic equations. Don't confuse that with geometry. So let's look how we know more things in the y direction. In the x direction, all we know is that the initial velocity and final velocity are constant. That's it. We don't know anything else. That's all we know. But in the y direction, we know initial velocity, we know my displacement, and we know my acceleration. So what I'm going to do, if I was working this problem, is I want to go to that list of kinematic formulas. And I want to say, okay, which one of these can I use to solve for time? And when you do that, you're going to find this formula. You're going to find that formula to be the best one. Okay? So let's do that to solve for time. I kind of have the work here, but I'm going to do it to show you step by step how to solve for this thing. Okay, there we go. There's my poorly written formula there. Now, right off the bat, I can eliminate a term and make my life a lot easier. This term right here, this first term on the right side of the equation, can be taken out. I don't need it. Why? Because the initial velocity is 0. Right? We know that. In the y direction, so I need to be sure I abbreviate well. In the y direction, the initial velocity is 0. The velocity at the top is 0. So anything times 0 is 0, so we're going to take this term out. We don't need it. So now our equation becomes this. Okay, you follow? Now, we're trying to solve for t. Why? Because t is the one that ties it together. Whatever I solve for in this deal in the y direction, time is going to give me something else to work with in the x direction. So we're going to solve for t here. We're going to keep doing that. So this becomes that. Because to undo multiplication, we divide. We divide by 1/2 a. Dividing by 1/2 a is multiplying by 2 over a. So That's why I got that. And now we got to get rid of this square root. And that's my equation for time. So we put all that in, we put our values in, and we get time to be 2.67 seconds. So I'm going to write that down somewhere. Because look, if this were my table of knowns and givens, I would then come up and add one more thing to it, 2.67. Or I could say time in the x direction is 2.67. Or I could say time in the y direction is 2.67. Now look, in the x direction, you know one more thing. You don't just know the velocity now you know the time. So can we solve for displacement? Let's see. I don't know. We'll find out. So we solve for time. That's the first part of the of the problem. So we're good. Okay. The next thing I want to do is find the range. The range is the displacement in the x direction. That's this. So I'm going to do the same thing I did earlier. I'm going to go back to my list of equations, my kinematic equations that I've provided for you, and then we're going to find out which one we're going to use here. Now remember, these are going to be simplified because acceleration in the left and right direction, the x direction, horizontal direction, whatever you want to call it, is going to be 0. So our equation list isn't, our equations aren't that significant. They're not hard. They're pretty simple. So I come back in here and I say, okay, which one involves time where I can solve for d of x? Well, it's my first one. So my first one says dx is equal to, the initial velocity in the x direction times the time. So luckily, this is just a plug and chug type problem. We know the initial velocity in the x direction to be 5 meters per second. We know the time to be 2.67 seconds. So we multiply those two together and we get 13.36 meters is the displacement in the x direction. So in this cannonball, what this means is if this cannonball is shot off of a cliff, let's say there's a boat down here, right? We're watching Game of Thrones, and somebody's shooting a cannon, or let's say we're watching Pirates of the Caribbean. That's more along the lines of a cannon, I guess. Down here, okay, here's my boat. To hit this boat, this cannonball shot at that velocity is going to travel 13.36 meters. So that boat has to be that far for it to be hit. Okay, so how far downrange it's going to go is 13.36. Wouldn't think I'd have to explain that, but that's a common misconception actually. That displacement in the x direction is is how far downrange it is. Okay, so remember that. So we found time, we found range. Now we're going to find velocity. We're going to find the final velocity. What velocity is it going to strike the ground with? All right, so here we go. It says final velocity requires a little more thought. Remember that velocity is a vector quantity. So we must state our answer as a magnitude and direction. Also, remember horizontal velocity is constant, therefore the projectile will never strike the ground at exactly 90 degrees. A projectile will never strike the ground at exactly 90 degrees. That means we need to look at the horizontal and y components that make up the final velocity. All right, so let's move on and see what this is going to look like. Okay, this looks scary. That's okay. It's not that bad. All right, so let's go. It says, let's look more closely at the vector VF to help see it better. Okay, so we exaggerated the angle here. This is just blown up, this circle, this blown up here. So what we did, or what we're doing here to solve for the final velocity, is we're going to take the velocity vector in the y direction, which is always going to be up and down, and the vector in the x direction, which is always going to be left and right. And we're going to solve, we're going to use the tip-to-tail method of vector additions to solve for this resultant vector, which is the final velocity. So I'm going to blow it up even more. Look over here to the right. Oops. If I could draw a picture. What this does is it creates a right triangle, okay? So where we have VFY and VFX. Um, sorry, I lost my train of thought here. Well, where the up and down component is the final velocity in the y direction, left and right component is the final velocity in the x direction. And the final velocity vector is this resultant right here that's going to strike the ground at some angle, theta. All right, so we already have the x component due to the fact that the horizontal velocity is constant, right? So we know the final velocity is going to be 5 meters per second in the x direction because the initial velocity in the x direction was 5 meters per second. So before we can find VF, we must find the vertical component, VF of y. We must find the vertical component of that, VF of y. So that's going to be our next step, to find the total final velocity, the velocity that the projectile strikes the ground with. We're going to have to find that vertical component there. So to find VF of y, remember that vertical motion is in free fall. So it is accelerated by gravity from 0 to some value just before it hits the ground. So this is going to go back to what we've done in the past. You've done this before. So to calculate it, we're going to use this kinematic formula. Again, I would go back to my list of formulas. I'll figure out what I know, what can I solve, and you would arrive at this. You'd find that was your formula that you needed to use. Then I'm going to substitute my values. See my next step here? This is step 1, step 2. My values. The initial velocity is substituted as 0 because the initial velocity at the top in the y direction, now think of this to be like an object in free fall, is going to be 0 at the very top. Okay, so that's why I put a 0 in. The acceleration up and down is going to be acceleration due to gravity, 9.8, and the time is what we found earlier to be 2.67 seconds. And we substitute these values into our equation, and we get VFY is 26.2 meters per second. Now, we are not done. That is helpful. That's helpful information and essential information, but it's not enough to solve it. Oh, what's happening? Sorry. It's not enough to solve the problem, because now we have to put this together and do a little trig and find the final velocity, the magnitude of this hypotenuse here. So let's think about, I want to draw my my vectors, my horizontal and vertical velocity, final velocity vectors. This one we said was 5 meters per second, right? And this one is going to be 26.2 meters per second. And the final velocity is this resultant right here. That's what we said earlier. Now this creates a right triangle. Okay, that creates a right triangle. And there's a couple ways you can do this. You could do Pythagoras, right? Remember Pythagoras, we can use the Pythagorean theorem. A squared plus b squared is equal to c squared. And we could solve for for that, doing that, using that one, where A and B and C. We can solve for this hypotenuse, the final velocity vector, that way. Or actually, yeah, I think that's about all you can do at this point. Yeah, to solve for final velocity, that's what we're going to do, because we're not given this angle yet. I was getting ahead of myself. Yeah, you would solve it using the Pythagorean theorem. My apologies. Pythagorean theorem. And then you could take what you know about trigonometry to solve for the angle at which it hits, theta. So we solve that, we put it into our Pythagorean theorem, we solve for C, and we find that the final velocity is 26 meters per second, or 26.7 meters per second. And remember that velocity is a vector, so it needs a direction. It needs a direction. We're not given an actual direction, so what we're going to do is we're going to find the angle that it strikes with, because that's about the only way we can describe the direction of this vector. So we're going to do that using trig, and we're going to use the tangent. Right? We're going to use the tangent function. Or more specifically, let me say the tan inverse function. So the tan inverse function, if you remember from our trig section in geometry, the tan inverse function takes a ratio. Let's say, trying to put this in words for you guys. I'm going to say opposite and adjacent. Takes the opposite and adjacent sides of the triangle and spits out an angle. Do not get this confused with the tan function that takes an angle and spits out a ratio. Okay, don't get confused. These are tan inverse function we're going to use to actually find the angle. So we take the opposite side of the angle, which is 26.2, and the adjacent side, which is 5 meters per second squared. Can't forget my units there. I wrote this incorrectly. There we go. Okay, so I'll take the tan inverse of that, and that will get me my angle. So how's this going to look in your calculator? On your calculator, you're going to hit the second button. If you're using a TI-84, which is what most of y'all have, hit the second button, you're going to hit tan, and it should display the tangent, the tan inverse function on the screen. Okay, it should say TAN with a -1. Hit second, tangent, and then type in the ratio, 26.2 over 5, 26.7 over 5, and that should give you your angle. And that will end up 79.2 degrees. 79.2, and that's our angle. Now, if it spits out something other than that, if it gives you some wonky number that's not even remotely close to that, right, some small number or something, it's likely that your calculator is in radian mode. We're not dealing with radians, okay? Our degree angles are degrees. So make sure your calculator is in degree mode to find the angle. All right, so now that we know the angle, how is our final velocity answer going to look like? Well, it's going to say 26.7 meters per second at 79.2 degrees. So that's telling me that this cannonball is going to strike the ground. If this is the cannonball, this is the ground, and this is the cannonball, it's going to strike the ground at 76.2 degrees to the horizontal. at 26.7 meters per second. Okay, this was a lot. I know. We're going to get a lot of practice. It's going to make more sense later. Just be prepared, be ready. Put your work hats on. Let me know if you have questions when you get done with this, watching this video. Go back, look over your notes, study, figure out why we did what we did, and be prepared for tomorrow. Okay, well, good luck. Be checking Google Classroom for more information coming your way on motion in 2 dimensions and projectiles. And also keep in mind, or be on the lookout, not keep in mind, be on the lookout for a fun new project that we're going to do. I'm not going to spoil the surprise, but anyhow, see y'all next time and keep on learning.